In this video, I'm going to talk about confidence intervals. So here's the big idea with confidence intervals. As scientists, we observe data and we calculate statistics based on the data that we actually see. But we never know the true population parameters in practice. So for example, we know X bar. We can compute X bar, the sample mean, based on the sample data that we see. But we don't know mu, the true population parameter that's underneath where X bar is coming from. But we want to make a statement about mu, a precise statement about mu, using only X bar in the data. We usually can't make an exact statement, but we want to say something about it. And so what we want to say is approximately where it is. So if we have our data and we have a X bar appears in some place, and then all our data points are somewhere around here, x's, 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 so the standard deviation is low, then we know that it's probably pretty likely that our true population mean is close to X bar in this case. So it might be the case that the true mu might be a little bit different. It might be over here, or it might be on the other side. We don't know. But it's probably not the case that the true population mean is way over here, right? So we want to identify a region on the line where mu is likely to be. So we would like to say that mu is likely inside here, this particular region that's close to X bar. So that's the idea of a confidence interval. We want to say where the true population mean probably is, and we do a confidence interval for the mean. So here's an example, because I like bicycles and I know something about them. So tires, people care about the weights of tires on the bikes that they ride, because lighter tires are faster, so people like that. So suppose you're an engineer at a tire company and you want to know how much your tires weigh. So a racing tire, you might get average weight of 250 grams and a standard deviation of 10 grams. There's a lot of variation because the rubber might be thicker or less thick in places, so there's variations in the weight. Suppose you computed that based on a sample of 25 tires. The central limit theorem says that X bar is distributed as normal with mean mu and variance sigma squared divided by n, approximately. So we can use this to build a confidence interval. In this case, our sigma squared over n, it's going to be approximately S squared over n. So we're plugging in S for sigma squared, our sample standard deviation, which is what we do in practice. And this is equal to 10 squared over 25. And that means sigma over square root of n, the standard deviation of our X bar, is equal to 10 over 5, which equals 2 in this case. 2 grams, that is. We're back to our units of grams. Consider now the probability density function for x bar. It's distributed normally, so we can draw it using something like this. We have a bell-shaped curve centered at the mean with 95% of the data lying in between plus or minus 1.96, which is the area where 95% of the probability density will lie. The area under the curve inside here is 0.95 or 95% here. And 5% is on the outsides, is this area, these areas over here, okay? So add those up and you get 5%. Inside you get 95%. So this is what the probability density function looks like for x bar as a random variable. Then we can plug in our standard deviation that we've computed over here. So this right here was equal to sigma of x bar, approximately. So plugging that in, we get a value of 1.96 times 2. Okay. So the true mu might actually be at something like, for example, we observed 250, but the true mu might be, suppose it's equal to 249. Okay, so we observe, and then this mu is about plus 4, so this is equal to 233 over here, and this is approximately equal to 249 minus 4, which is 245. This is 253. So the value that we actually observed for the mean was right here. X bar, which is equal to 250. Okay, so we could have gotten anything. We could have gotten something inside this 95% interval, or we could have gotten a value x bar equals, say, 254. It's just less likely that that happens because the probability density is lower there. So we can use this idea to build our confidence interval. The thing is, we never knew or know mu. So we turn this on its head, and in this case, we go down here and we can use the same curve. So we can go down here and draw the same curve idea using x bar. So here these are plotted on the same, or I intended to plot them on the same vertical axis. So we go down here, and this is equal to x bar, which is equal to 250 now. And then we have this area 95% area by subtracting and adding the same points so that we get the same 95% coverage. So in this case, it becomes 250 minus 4, which is 246. And the area over here plus 1.9, so it's about plus 4. It is approximately 254. So using this, we would say, so and then suppose that the true mean is still in the same place that it was before. Again, it's 249 is mu. So now we have these endpoints, and the idea is that 95% is within these limits between 246 and 254. So we say We say that a 95% confidence interval for mu is the interval from 246 up to 254. So this represents the region where we think that mu probably lies. So in this case, it did happen that if we suppose that mu is 249, it did happen that it was in here. But it could be the case that it doesn't. So these are commonly misunderstood to be the probability that that is where mu lies. And that's not the case. It's not a probability. A confidence interval is not a probability. The interpretation is that if you repeated this same procedure of constructing a confidence interval many times, then 95% of the times you would get the true mean contained in an interval like this. That's the idea. So there is one technicality here that I forgot about when I started writing this problem, and that's that having n equals 25 here. With the central limit theorem kicks in at n equals 30. So n equals 25 is a little low to be doing this, but the idea is the same. Like, you could take n equal 35 and do the same thing. And 30 is not really a super hard and fast rule, but it would be better to have more if I'm using this large sample approximation and appealing to the central limit theorem as I am here.